I'm going to make up that lecture this Thursday. I'll have an extra hour after. So I don't know, in case you didn't receive that notification. Is that possible? Can you do that? It's after, so it's 3 to 5, just like this. So the same block. I hope that's convenient for people. Okay. So last time we talked about some history of shock theory and some reasons why one might want to study viscous shock stability. But you could also, for those just joining in, you could just start here. We're going to talk about stability of viscous shocks, which is interesting, clearly interesting by itself. Okay, so we're going to study, so again, here's the equations. Okay, so we're doing one-dimensional flow, and we're doing a scalar unknown, W. So the idea is I'm going to try to present the ideas in the simplest possible setting, but using techniques that apply in the most complicated setting. They go over almost unchanged, so it seems wise. Okay, and a standing wave solution. So without loss of generality, a standing wave, W of xt equals W bar of x. And the limit, as the argument goes to plus or minus infinity, is a constant solution. And this limit is exponentially fast. In several derivatives. And this we found by looking at writing down the standing wave ODE, and we see that it connects two rest points typically, which are non-degenerate, therefore you get exponential decay. Okay, why is it without loss of generality? More generally, we would look for a traveling shock wave with a certain speed, but if we simply change coordinates to a frame moving with the shock, it now becomes standing. It changes the equations, but only modifying f. It still has the same form. So let's take it to be stationary from the beginning, because that's the first step in any case. Okay, now we'll introduce nonlinear perturbation, V. Okay, so V will be defined as W minus W bar, or of course, equivalently, we can write W equals W bar plus V, which we'll use below. And we want to show, well, we'd like to show this perturbation goes to zero or is bounded or, some kind of stability. Okay, so let's subtract both solutions satisfy the same differential equation. So if we subtract the W equation minus the W bar equation, then we get, now let me see, I want to, how's that size of writing for you guys out there?
The first line and the second line are good. Even the third line, the fourth line gets a little small to read.
Okay. All right, bigger. Okay, so we're going to take the W equation and we're going to subtract the W bar equation. And then, okay, so for all linear terms, we just get, so we get dTV, that's dt of W minus W bar, plus dx, f of W minus f of, sorry, let's write it like this, f of W bar plus V minus f of W bar equals dx squared V. And I'll rearrange this as dt V minus negative A bar v minus dx of negative a bar v minus dx squared v equals, and on the other side, I'll put dx of f of w bar plus v minus f of w bar minus df at w bar v, where a bar is defined as df of w bar. So this is the same. This is just canceling this term. And now we'll call this whole thing. Okay, so this is plus. Let's see, did I get that right? Yes. We'll call this LV because it's a linear operation on V. It has derivatives. Whoops, let's see, let's try it. Yeah, that's right. It has derivatives, so it's not a bounded operator. So we have in mind, I should mention, we have in mind H2, right?
The L contains the dx of the outside.
Let's see, the L contains the dx, yeah. Everything inside the bracket.
A bar is the differential of f w bar.
Yes, yeah,
Okay.
yeah. So these are in fact the same term, these two.
When you write df, you mean df derivative of f respect to dot.
Yeah, with respect to, yeah. Mhm. Yeah. Okay, so I'll call this, so I'll write this as, rewrite as dtv minus lv equals script n of v, where this is dx of little n of vx, and little n and dx of little n are order of v squared. And that comes from just Taylor expansion. We could write this as, we could use the integral remainder formula to write this as a quadratic form in V. And looking at, I should have mentioned, W bar has many derivatives, as many as you like, assuming that as many derivatives as little f has. And we'll assume it has enough, okay, to get this. Okay, so, all right, so that's what we have. And this, so I'll call this the, so this is the nonlinear perturbation equation. But this part, dt v equals, or minus lv equals 0 would be the linearized equation. And we're asking, what is the growth or decay of little v, depending on the initial datum, v of 0. And that's our question to investigate. Okay, so what I'm going to start with, but I should say, let's see. Okay, so what kind of an operator is this? L is linear. It's linear. It's unbounded. It's exponentially asymptotically constant coefficient. That's the type of operator it is.
The decay of v relative to
V of 0, I'm sorry, V of 0, the initial data.
at time equals 0.
Yeah, yeah, times 0. Yeah. 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 Yeah, so I'm going to, sorry, if I put only one argument, it means time. And I'm considering v as in h2 of x. Yeah, yeah. Which is skipping ahead a bit, but anyway. Okay, so how to treat these things. So it's variable coefficient, so we can't just use Fourier transform. We're going to do other things. So let's review. I'm going to do the ODE case, and I'll show you the structure of the argument I'm going to use. And we'll just add things to this argument as needed, because some of the things are going to not carry over to unbounded operators or infinite dimensions. So we have to do something else. Yes.
Asymptotically constant coefficient is that.
Yeah, CC is for constant coefficient. Yeah.
Is it that for because W is exponentially?
Yes. Yeah. So W I should have redrawn looks like this. W bar. And it interpolates between W minus and W plus, and it does so it converges to these end states exponentially fast in 2 or 3 derivatives. That's probably all we need, but as many as we want, as many as derivatives as f has.
And is it smooth?
Yeah, very smooth. Yeah, it's smooth because it was the solution of a second order ODE. We talked, this is what we were, one of the things we talked about at the end, but it's now a bit long ago, but it was that it solves a first order ODE in X.
Okay.
And it connects two non-degenerate rest points. It's a scalar ODE, so you just exponentiate and you can see all these things almost explicitly. But yeah, so it's very smooth and it converges very fast to the end, to the states at the end. So you could think of it, I often draw this picture, there's sort of a shock layer, and then these flat regions out near the ends and near plus and minus infinity, where it's basically just a constant coefficient equation. And we could understand that by Fourier analysis and things like that, because what's happening out here is constant coefficient. Somewhere they interact, though, that gets tricky. Okay, so I'm gonna. Okay, any questions from the online attendees? No, any questions here? Okay, thanks for the helping clarify. So we're gonna do the ODE case as a motivation, and we'll do two things. A, we'll convert spectral information and to linear decay. And then B, we'll do a bootstrap, or I usually call it continuous induction. To give a nonlinear decay. And for those of you who watched the winter school lectures last week, John Anderson mentioned this bootstrap technique. It's exactly the same as what he used in his lectures for going from linear to nonlinear stability. Okay, so the problem. It's again dt minus LV equals n of V equals order of V squared. This is the problem we want to look at. But now V is just in Rn. And L is an n by n matrix. N is an Rn valued function. So they're just functions. That makes it easier. But this is the first thing you do. And you use, okay, so first thing is you use the Jordan decomposition this is the standard way. We know that this is R is a matrix with columns of generalized and genuine eigenvectors. L is its inverse, and J is block diagonal with Jordan blocks, and each Jordan block looks like an eigenvalue down the diagonals, and then ones on the super diagonal, first super diagonal. It's upper triangular. Okay, so this is Jordan block. All right, and okay, so we can exponentiate. So we know that e to the jkt is what? Well, this is aj times the identity that commutes with everything. So we get e to the ajt times e to the njt, where nj is the nilpotent part, which is just ones down the first super diagonal. Okay, and that's familiar. This can be computed by a finite series. E to the nt is identity plus n squared over 2 plus the series for e, but it truncates because every time you multiply n times itself, it moves this the diagonal of super diagonal of ones up by 1 until it disappears. So n to the s equals 0, and where this is s by s, sk. Okay, so that's how you can compute this, and you find out what the familiar thing. It's therefore e to the akt, and then we get ones down the first diagonal, then t squared over 2, etc. Just the series for e, and this is order of 1 plus t to the sk minus 1, because that's the highest power of t. It will be in the s column, and it will be t to the s minus 1. Okay, so some algebraic growth times exponential. Well, we hope it's decay, right? Okay. So what we get is a bound on e to the lt is less than or equal to the matrix norm of the matrix of right eigenvectors times e to the times the left eigenvector times 1 plus t to the sk minus 1 times e to the the max over k of real part of a k, t. So putting all together, less than or equal to c e to the, let's call this maximum value theta, e to the theta plus epsilon t, c epsilon, any epsilon positive. Because adding any positive epsilon is enough to capture this algebraic growth, right? The usual thing. And then we have, okay, these all go into the C. And then we have, here's the e to the theta t from the maximum eigenvalue. So we get, if all the spectra is negative, we will have exponential decay.
Sorry, I don't see very well. So we
Oh.
need to write below the big matrix, below the matrix.
Oh, sorry.
Up there.
Oh, up there. Okay, let me bring that over to the other board. Yeah, that's it. Let me bring it to the other board. That's better. Okay, so they'll bring it here. Yeah, so it's e to the LT operator norm is bounded by the matrix of right eigenvectors, matrix of left eigenvectors, e to the theta t 1 plus t to the s. Yeah, let's just write a star. Minus 1. Okay, where a star is the AK with maximum real part. So that just comes from taking norms everywhere. And then I'm going to summarize this as this resumes to C e to the theta, a star real of a star plus epsilon times t, and this would be a C depending on epsilon for any epsilon positive. So I have an exponential bound, and it's almost at the rate of the maximum real part of the spectra. I can just bump it by epsilon and I'm okay, but I might have to pay with a big constant if I take epsilon small. So this is standard. And so if I assume that all the spectra, the AKs, have strictly negative real part, this gives me an exponential linear decay. So this is the familiar necessary and sufficient condition for linear decay for constant coefficient ODE. And now, okay, but now I want to get a nonlinear result. So that's the end of part A, which was to go from spectrum to linear estimate. And now let's do part B, which is the bootstrap. Okay, so we'll assume that e to the LT is less than or equal to a constant times, let me make sure I use the same, okay, e to the minus theta t, theta positive. So I choose some epsilon, and I get some exponential amount. Okay, so now I'll define alpha of t is defined to be the supremum for 0 less than or equal to s less than or equal to t. How's that writing there? Okay, of e to the theta t theta s v of s. Okay, that's it. Okay, proposition. This is the bootstrap estimate. So if alpha of t is less than or equal, no, not if, just alpha of t is less than or equal to a constant times v of 0 plus alpha of t squared, so long as the solution exists. And bounded by a constant. Any constant. Oh. So normally we would do this by a contraction mapping argument, working in a weighted space, very much like alpha. So this is hiding a contraction mapping type argument, but it's more flexible. And you don't have to worry about finding the correct spaces. You can use this argument without spaces.
But when we say assuming the solution exists and is bounded, it's the V of t, the V of
Yeah, the V.
V is bounded.
Yeah.
And V is
And
the matrix. It's a column vector.
yeah.
N dimension.
Yeah, it's an n-dimensional column vector. And remember, even the nonlinear ODE is pretty harmless. It's linear constant sorry, it's not constant. What I'm saying, that's not linear, but it is certainly Lipschitz smooth and things like that. It's got existence and uniqueness and a Grunwald estimate. So we have an existence and uniqueness and continuous dependence theory for free by standard ODE theory and Picard iteration. So, and that's important, right? You have to do this kind of bootstrap argument. You do need to have a short time theory in hand. You have to have continuity. Okay. But not for this estimate, but to continue to get something out of it. Okay, so let's see. So let's prove this. Okay, so let's see. Well, maybe before. Yeah, I'll just prove it. Okay, proof. So variation of constants or Duhamel formulation, whichever you prefer, gives the solution formula V of t is equal to e to the LT V of 0 plus the integral. Sorry?
Are you assuming V small or
I don't believe I even need V small for this one. Let's see. No, at this point, I don't need V small for this. Normally, yeah. Let's see. I don't think I do. I think I just need it bounded. We'll see in a minute. Yeah. You're right that typically in such arguments, we assume V small because we need to, but here I don't think we even need to. Let's see. Yeah, where did I use boundedness? I said N was quadratic order. Of course, that's only true for bounded V. If V, because it's just a Taylor expansion. So it would depend on the size of the third derivative. I'm sorry, the second derivative, which is bounded only if V is bounded. So when I write, let's see. So let's see, so far, no, this is all correct. No, so here is N. This is N of V. That's just the formula, standard. So now I want to estimate V of t, or yeah, so V of t is less than or equal to e to the theta minus theta t using the operator norm of e times V of 0 plus integral from 0 to t of e to the minus, see, there's a constant out in front of that in my bound. So there's a constant here, minus theta t minus s, and then times norm of n, big N. But the norm of big N is like another constant, this will be a universal constant, and I'll get V of s squared ds. But now I'll write this one using the definition of alpha. let me go back here and just note that this gives a bound. This says V of S is less than or equal to alpha of t e to the minus theta s for s less than or equal to t. Okay, so let's see. This is okay. So I'm going to write this as this is less than or equal to integral from 0 to t e to the minus theta t minus s e to the minus 2s ds, and what needs to go out here is an alpha of big T squared for any big T, so T less than or equal to big T. Okay, so alpha of S is going to be the soup, well, the max. 0 less than or equal to S less than or equal to T of e to the theta S times
It's small.
small t. Okay, so it'll be e to the theta S times V of S. But now I'm exchanging the roles of T and capital T. So I'll use this bound for little t equals S and big T equals little t. Sorry about that. I didn't plan that super well, but this would be so e to the minus theta S V of 0 plus alpha of t squared. That was formerly in this formula, it's alpha of capital T, which was not written too clearly. This is a capital T here, squared. And then we have a C out in front. Sorry, we have a C here, and we have I'm going to move this below. C alpha of t squared, integral from 0 to S, e to the S minus tau, e to the minus theta S minus tau, e to the minus 2 tau, d tau.
The V upstairs.
This is V of S. That's what goes in here in the definition. It's e to the theta S times V of S. And I take the supremum. But I have a bound on V of S coming from the bottom of the board, which is this. Let's see, on the take the supremum over S, and here alpha of thank you, alpha of t. That's good. Yeah, now it makes sense.
Then just here there's like minus 2 tau
Theta, probably.
Yes, 2 theta tau. There we go. Yeah. Okay. And now we're going to cancel these, and this is a theta s, right? Yeah. So we're going to cancel those. We get the supremum, 0 less than or equal to s less than or equal to t of, okay, first term exactly cancels, v of 0. That's expected, right? We just put it in and took it out. That's what the norm, this measure alpha was designed to capture. The next one, though, becomes a constant times alpha of t squared. Okay, and now we have, okay, so we have, this cancels that. But that leaves something, and that leaves integral from 0 to s. And this one partly cancels that. It removes the 2. E to the minus theta tau d tau. And this is convergent. So bounded. That's all I'm doing. And so that's less than or equal to a constant times v of 0 plus c alpha of t squared. Done. So this is just reflecting the fact that exponentials work very well with this kind of thing. You can check if you had an algebraic rate of decay and you were trying this argument. Well, it may or may not work. It depends on if you have a fast enough algebraic decay, it still works. But there's a critical value. If it's a slow exponential, a slow algebraic decay, basically you're left with something like your algebraic decay rate over here. It has to converge, and it won't converge if the rate is too slow. Okay, but I'm just showing you the basic one, the basic argument where we're trying to reprove Lyapunov's theorem that a sufficient condition for nonlinear exponential decay is linear exponential decay, which in turn follows by spectral exponential stability. Real part of spectrum strictly bounded from 0. So we've gotten up to the Bootstrap estimate, and there's a very small step now to finish. But let's pause here. This is the key estimate. Okay. So, all right, I think I'll give up this board. We're okay with this board going away. And now the corollary is what we want. The corollary is nonlinear stability. Right. And where did I use boundedness of V in there? It was right at the beginning. I just erased it. It was when I estimated n of V, norm of n of V, by order of V squared. That's exactly where I used it, and only there. Okay, so for now, but for the nonlinear stability, I do need smallness. Okay, C, okay, now C as in proposition. Give it a name, dagger. The solution, V of t, exists for all time. And, well, I guess it exists and bounded No, it exists for all time. That's not clear. And it satisfies exponential decay. So V of t is less than or equal to no, better than that. And alpha of t is less than or equal to 2c v of 0, which implies that the solution v of t is less than or equal to alpha of t e to the minus theta t equals 2, which is less than or equal to 2 capital C v of 0 e to the minus theta t. So that's nonlinear exponential decay. Well, let's forget about that. At the same rate. So we actually lose nothing here. Okay, so proof of the corollary. So this is this is like the last part of John's talk. Let's see, I think I'll save that and I'll go. Okay. Proof of the corollary. Okay, so alpha of t exists and is continuous so long as v is bounded. What? This is the basic existence uniqueness theorem for ODE. The local existence and continuation theorem for ODE. And I'm going to follow this pattern throughout. I'm not going to prove any local existence and uniqueness theory. I'm just going to always assume we have it. But for the equations we look at, it will be clear. They're standard results. So here, this is a standard result. Okay, now we'll show. Whoops. That, okay, the basic driver is alpha of t less than or equal to twice C3V of 0 implies, so 1 implies 1 prime. Alpha of t is less than or equal to 2. Oops, what did I do? Which was, implies, sorry, strict, here we go. Strictly less. That's all we need. The only difference is the inequality. Because if this is true, then we can never reach this upper bound. Because if we do pass this bound, there would be a first time we reach it. And at that first time, it would be a contradiction.
It's not that you can also do it by from the proposition. You make a picture of the function alpha minus c times the parentheses, and then
Yes.
v0 needs to be small enough to stay below, and otherwise you have.
That's a very nice way of doing it. Yeah, you you can write write this as a quadratic and graph it and see that it can't escape out of a certain point. Yeah, that's I'm familiar with that. I like that too. Yeah.
It's probably the same idea.
It's like a clever way of doing this. And this is the same as actually this is the one I prefer, and this is the one that was mentioned in John's lecture. So they're exactly the same. I think it's more simple-minded. It's not as clever.
Sin-
Yeah, especially in the works of the Japanese school with Ukai, Kawashima, and Masumura. They use that because it's very elegant. A way to do it, but okay. So, but if we show this by contradiction, one we must have actually, in fact, one prime holds always. Otherwise, there would be a first time where it fails. But at that, by continuity, one would hold instead of one prime. But one implies one prime. So there's a contradiction. But okay, and then and then we would have, so therefore, yeah, it's actually I could have put strictly less than, but it doesn't matter. And this is plugging this in for a definition of alpha, we get this bound. We get exactly the kind of exponential bound we would want. And it's almost no worse than the linear one. It only differs by this factor 2. So we lost almost nothing in this passage from linear to nonlinear. Which, that doesn't always happen. Okay, so that is Lyapunov's theorem, stability theorem. I think it's the first method or the second method. The one without the Lyapunov functions, the ones where you do it by analysis like this. But substituting for fixed point contraction, this Bootstrap, which is, you'll see it's more flexible in some other. You can use this in many situations without having to find a nice space. Finding the space to contract in, that can be cumbersome. This is a little easier. Okay. So, any questions? That one at least we can do. Okay, but now let's see. What are we going to do for our operators, or more generally for an unbounded operator? What would we do? I mean, the very first step is we have to think about the spectrum. And our first step was to do a spectral decomposition. So spectrum and spectral decomposition. Of an unbounded L. That's our, we're going to pause here and think what could that be?
Yeah, we have finished the ODE.
We finished the ODE. Now, so that was our motivation, and we introduced two key ideas. One is a kind of a general way of thinking about getting from spectrum to linear bounds, but that will have to be improved. The Bootstrap, that will be always there, but we're going to have to add a couple more ingredients. I can tell you also, I can tell you right away. So we have order of dx, n of v. So we have n of v. Our nonlinearity, it loses a derivative. That puts us in a different space. It's not O of v squared in H1, H2 norm. Because right, we can this is n and x, sorry, like v sub x. We can pull out one by Sobolev embedding, but the other one still got too high a derivative, so it's not going to be nice for us. We're going to lose a derivative typically. If we go to a high enough norm, let's see. No, we're just always going to lose a derivative. H2 is an algebra, so the n, that's O of v squared, O of norm of v squared. But now we have an extra derivative. So we're always, so that's something. We're going to have to make up some derivative loss. So that'll be another thing to add in. So that we'll have to adapt, but that's a side note. Just it's easy to tell. So there's something to do. But there's also something here. So what kind of spectrum could we expect? So let's try first example of unbounded operators, bounded domain. And we could think of Fredholm theory. So compact operators with a compact inverse somewhere. And we get lambda 1 less than lambda 2 out to, we get an infinite sequence of discrete finite multiplicity eigenvalues. So they're truly eigenvalues. They have eigenvectors or generalized eigenvectors. They behave just like the finite dimensional case. However, there are infinitely many of them. So, okay, that's one point. Second example. What about a constant coefficient? Or, oh, sorry, no, I wanted to say, let's see. Okay, yeah, or, okay, we could do the interval 0 to pi, periodic, boundary conditions, constant coefficient. Okay, that's the same. We could do that by Fourier series, and we get something very much, well, it does belong to the Fredholm case, but maybe it's more familiar. Third example, constant coefficient on R. So we can take the Fourier transform to understand the spectra there. And now the spectra is continuous. It has no eigenvalues, just continuous spectrum. So things are getting different. And then, okay, I could generalize this for variable coefficient self-adjoint operators. We could do the spectral expansion theorem of Gelfand or others, and we get a combination of point spectra and continuous spectra, where the continuous spectra are like a generalized Fourier transform. Okay, so and the point is that all of these things could exist. I claim the problem that we're looking at, it doesn't fit any of these paradigms. It's different. And we're going to do it very, the only way I know to see it is just by explicit calculation. It's a very nice example that one can work out and see another possibility for spectra. Neither continuous nor point spectra. It's essential spectrum, but it has a full two-dimensional measure rather than being on a curve as continuous spectrum or points. So it's supported on a spectral measure supported on the plane. But we'll see that later. Okay. All right. We could. So now what about these? Even for the ones that I say are not sufficient to cover our case, but what if we were trying to estimate, to change spectral information into an estimate? Even for these cases that I'm saying are more favorable than ours, well, we wouldn't want to do what we have just done. We certainly wouldn't want to do Jordan form. Because even in the finite dimensional case with a large dimension, you don't want to do that. Like for numerical analysis, this is a bad idea. That's known because you have to estimate, we're estimating the R and the L, it's the condition number of the change of basis can be very bad. And oh, well, okay, it's not bad or good. It's true. It's a real estimate, but how do you find it? Not only that, Jordan form is not robust under small perturbations. So it's not going to give you a very convenient estimate if you work this way. So we're not going to do that. So, okay, so back to ODE. We're going to do it different way. The better way is to use inverse Laplace transform. And resolvent bounds. So this is even the case just for ODE, this is better. And if you look at an engineering textbook, the whole ODE will be done by this, by Laplace transform. And you won't have Jordan form. So I'm going to do some more ODE. Okay, but I stop here for a break. That's perfect. And then we're going to do Laplace transform.
So Kevin, this is, I don't know if you met him, it's another Federico.
I know we have, we're multiplying Federico's. Yeah, yeah. We met before the class, but you can tell me what
Thanks.
yeah, that's nice.
It's funny that we have two Federico. We can ask that complex.
It's very rare, right? That's how people.
All right. Okay, we're taking a break. 5 minutes. Okay, so we're going to revisit the ODE from a Laplace transform point of view and try to convert spectral to linearized estimates. So once again, we have dtv equals LV, and this is a matrix, and this is a vector. And in particular, it's bounded. So we easily find that V of t is less than or equal to a constant times e to the matrix norm of L t v of naught, v of 0. So that's a very terrible bound, but we could have a bound. And the idea is we're going to now improve this bound. But okay, so this is just a starting point. Okay, so for any gamma bigger than L, norm of L, we'll take lambda, we'll denote it as gamma plus I tau, we can take the Laplace transform. So the Laplace transform. And I'm just going to denote it by a check, the check of lambda, instead of the hat for Fourier transform. And this is the integral from 0 to t, e to the minus lambda t, v of, sorry, minus lambda, oops. No. Infinity, lambda t, v of t. There we go. Right. So this is well defined because e to the minus lambda t norm is less than or equal to e to the, let's see, what am I saying? Is e to the negative gamma t, and then so put the v in there. E to the minus gamma t, v of t, but this by our assumed bound is less than or equal to e to the t times theta minus gamma. Sorry, v of 0. V of t, and this is with a v of 0. There we go. But this is negative. Did I get it backwards? Yes, this is negative. So it's exponentially decaying. So this is an L1 function, right? We're basically taking the Fourier transform. This is what it's saying. This is the Fourier transform in tau of v gamma defined as e to the minus gamma t v of t. For t positive, 0, 0 otherwise. Okay, and so I'm more familiar with Fourier transform, so this makes me happy. We're Fourier transforming an L1 function.
Fourier transform of big gamma defined like that.
Mm-hmm. So if you look here, that's exactly what I have. And I'm extending as 0 below to make it a Fourier transform. And it's fine. Okay. So I get the inverse Laplace transform formula is that v of t can be recovered as the integral from gamma minus I infinity, gamma plus I infinity of e to the lambda t, v check of lambda v lambda. And that would be in Fourier transform. This would be the integral from minus infinity to plus infinity of e to the I tau v gamma hat of lambda of tau v tau.
And t must be some tau t.
Yes, I tau t. Thanks. Yeah. Yeah. Right. This would be the same. Now, okay, but you may notice we actually need something here. We need to add something. This is a principal value integral. We don't have to worry about the small frequencies, but it should be the limit as r goes to plus or minus infinity of the integral from gamma minus I r to gamma plus I r. That's what I mean by principal value here. That's the place where you have trouble with, you will not have absolute convergence necessarily. And here's roughly why. When we take the Fourier transform, well, on the t side, it's very good. It's L1 and it's L2 and it's everything, it's L infinity for that matter. But that doesn't help us with the transform. We have, so what I'm doing is that V gamma is in L1 intersect L2, and that goes by the Hausdorff-Young inequality for Fourier transform. That means that V gamma hat of tau, or of tau, is in L infinity intersect L2. That's not giving, this one's not giving me any help with convergence. And this one neither, but it does, because we have all along a Parseval identity that tells us what we can do is truncate this to make it, just truncate it by capital R. Now it's L1, gives us a perfectly well-defined Fourier transform, and we'll take the limit. And the limit is bounded using Parseval's inequality, or in Parseval's equality, identity, by the L2 norm. It's converging in L2. It's kind of a funny thing. So this is only, so even though this is in all norms, the other one's in high norms, L2 through L infinity. And okay, and we have only this. Okay, next thing, we notice the, okay, so now we want to use the equation. But first we note the familiar fact that if we take dt of v and take the Laplace transform, that's the integral from 0 to infinity of dt v of e to minus lambda t dt v of d dt, and we'll go by parts and get e to the minus lambda t v from plus infinity to 0, and then plus, because there's a minus here, plus the integral of e to the of lambda e to the minus lambda t v of t dt. This is lambda v check, and this vanishes at the upper end, and at the lower end, this becomes 1. So this is just minus v of 0. So yeah. This what the engineers all know because they studied in their textbook. Okay, so now we use the equation. So dt v minus lv equals 0, therefore gives us that lambda v check minus v of 0 minus L v check, and this just passes through as a linear, bounded linear operator, passes through the integral. So the transform of LV is L applied to the transform of V, and that's 0. Or we have, let's put it right here, or lambda minus L V check equals V of 0. And this gives that V check is equal to lambda minus L inverse V of 0, where lambda minus L inverse exists. So, and for example, for real part of lambda equals gamma greater than theta, greater than L. Because if we're larger than the matrix norm, well, for sure we're away from the spectrum. This is invertible. It's all matrices. Okay, and so that will give us, so combining this with the inverse Laplace transform, we get, okay, now I'm going to write the solution operator as eq dlt. We know that exists. V, sorry, eq dlt v of 0, so that's v of t, equals principal value of gamma minus I infinity, gamma plus I infinity, e to the lambda t, lambda minus L, inverse v of 0, d lambda. So this is for gamma greater than theta. Greater than L. Okay. So, okay, let me look a little bit closer at, okay, so the resolvent is just this operator lambda minus L inverse, this matrix actually in this case. And, okay, so it's very concrete in this setting. We can compute it by Cramer's rule. This is L minus lambda adjugate matrix. I don't know if you use this terminology. It's the transpose of the matrix of cofactors that goes in Cramer's rule divided by the determinant. Sorry. This is, of course, lambda minus L over the determinant of lambda minus L. And this is the characteristic polynomial. It's degree n in lambda. The matrix of cofactors, these are determinants of size n minus 1. So it's degree n minus 1 in lambda. So from that, we can see a couple of things. First of all, it's meromorphic. It's analytic except at the spectrum. And where it's not analytic, it's a pole of finite order, because we're just dividing two analytic functions. Okay, so meromorphic, meaning finite order. Discrete poles, isolated poles, finite order is the definition I have in mind, and it behaves like 1 over lambda for large lambda. So the asymptotics are really easy to see here because we've got a lambda to the n down here, lambda to the n minus 1 up here. That's it. So it has a nice decay to help us. Okay, so those are a couple of properties. Now let's write down what it looks like, because we can do that as well and get a couple more properties. But here, I'm going to use the linear algebraic fact again of Jordan form. So lambda minus L inverse is the inverse of R, J, L. And here J is the little j, 1 through J, L, a matrix of Jordan blocks, and the JK are these blocks A, K on the diagonal, ones on the super diagonal, else everywhere else 0. This is an upper triangular matrix. So we can write this. Let's off of the side. Let's continue here. That is R J inverse L. And J inverse is easy to compute by inverting on each block, diagonal block, because it's an upper triangular matrix. We can just write this down. I hope these are minus ones. Sorry, minus one. Minus L. Yeah, we're subtracting. This is this is lambda minus AK, lambda minus AK, and minus 1. We subtracted the Jordan block. I forgot that. Okay, so lambda minus JK inverse is, well, we know it's 1 over lambda minus AK down the diagonal, since it's upper triangular. And what it turns out to be is 1, so 1 over lambda minus AK squared, 1 over lambda minus AK cubed, etc. to the S minus 1, where this is S by S, and then it's filled in. These are equal along diagonal bands. So it's quite explicit. The J, this is lambda minus, J does not, this should be, right, lambda minus J. This is what my mistake, yeah. And J is that, yeah. So this is what we need to invert. Okay, and we see exactly how it looks. And, okay, so.
And the second line, so R minus 1, L.
This one here?
Just below the, yes.
Oh, this is a script R, J inverse L. Oh, it's lambda minus J. I'm having trouble with that. Then I'm dropping the lambda.
L in R.
Oh, they're inverse. Yeah. Yeah. It's basically, I'm basically changing coordinates to the Jordan coordinate. And then L and R is just are sitting there. But that's nice because it allows me, this one I can do so explicitly. And what do I find out? Let's see. Find out various things. Well, yeah. Yeah, okay, right, here we go. Okay, so now what happens? So here I'm depicting in the complex plane the spectra of L. So suppose suppose the spectra is all to the left of the imaginary axis. So we're in the good situation of a spectral gap that we previously, just by explicit calculation on the Jordan form, we showed was exponentially decaying. We'll get exponential decay here in a different way. So we use that V of t is this principal value of gamma minus I infinity to gamma plus I infinity e to the lambda t lambda minus L inverse d lambda. Okay, the first thing is, and let's call this first one, okay, let's call it A star, the top one, as we did before. So I claim that this is equal, and let's call this one gamma star bigger than A star, just anything bigger. I claim that we can move the contour to the integral from gamma star minus I infinity to gamma star plus I infinity, and still maintain the still maintain our formula. That this is still valid if we move. And here was, and this was for gamma greater than L. So here's operator norm, say. It might be large compared to the spectrum. We don't know. We don't care. But I claim I can move. This is the contour initially. Here's L. And here's the original gamma that we took, something out here. Anything bigger than the operator norm of L. But I claim I can move. And how can I move? Well, for any fixed t, I have the integral from gamma minus IR to gamma plus IR is equal to the integral from gamma star minus IR to gamma plus IR times, okay, what does the integrand look like? Well, e to the lambda t, that's bounded. Because in the imaginary part just gives a modulus 1 contribution. The real part gives something that's bounded because t is fixed. And lambda and gamma is only moving between two fixed points. So this is bounded, maybe large, but it's bounded. And then lambda minus L inverse, but this is like 1 over lambda. We just showed. This is actually decaying like 1, that's the asymptotics. So as we take, so this is like 1 over R. C of t over R. As we take the limit, this goes to 0. As we take the principal value, taking big R to infinity for fixed t now. If we do that, these two integrals, contour integrals either converge together or not at all, because they differ by an amount going to 0, something of order 1 over R. So that's standard, like complex analysis, residue theory and moving contours. But we need to have some decay. Well, we got that from the structure of the matrix. That was a cheap way to get the decay.
Lambda minus L minus 1 is smaller than 1 over tau, you said?
Yeah, 1 over tau. Yeah. Tau is the imaginary part, which is the dominant part because the real part is fixed at gamma. So when I take large asymptotics, this integral is basically in tau. Because I'm integrating, remember, I'm taking a limit, so I'm taking the limit as big R goes to infinity of a bounded contour of size R. And I compare the two, and the difference is size 1 over R. So these limits are equal. If one of them exists, the other does. So that now allows me, that's the main point, is now, as often in these sort of residue type calculations. And, but I have to assume, you see, but I've passed through many points. I need that this resolvent exist and be bounded everywhere in between. So that means I cannot cross the spectra. I could have a perfectly nice bounded resolvent over here, but the two formulae would no longer be equal. And that's going to be important as well. But first, let's just see what we get here. Okay. Okay, maybe stop there for a moment. So have I convinced you that that I can change the gamma? Yeah, I can move it all the way down until I hit the spectrum. Hit the largest real part of the eigenvalue. Okay, but now okay, now we come back here. Okay, now I would like to bound. Okay, so my bound would be I have principal value integral minus I infinity to plus I infinity e to the lambda t. Actually, now I might like to write e to the gamma t, gamma star t, integral e to the I tau d tau. It's the same. And lambda minus L inverse V of Z. And I can put the V of 0 out here if I like. Okay, so now let's look. Here's the decay estimate I want. I just need this bounded. The part in parentheses. Okay, and let's look at I've explicitly written down the resolvent. Everything in sight, and lambda is bounded away from AK because the real parts are different by assumption. So first of all, it's bounded everywhere for finite lambda, finite tau. I only need to worry about convergence as tau goes to infinity. I only need to worry in one part, the diagonal entries, because these are all absolutely convergent. They're 1 over lambda squared, 1 over tau squared. They converge. This is the only bad one. But look how explicit it is. It gives an alternating sum that one can compute quite explicitly the convergence rate. But if I didn't have the PV, it doesn't converge. So that's a nice example of basic example of this. Okay. So I'll say, but it's explicit. And okay, so that's an exercise that you should do. Everyone should do that. I keep doing it myself over and over to remind myself how this works.
By analyzing this diagonal, we'll be able to prove that this integral is bounded for all tau?
Yeah, for all, sorry, for all, okay, so uniformly bound, it's really from minus R to R, right? And we're gonna let's, I think it's better to write it out. Limit as R goes to infinity. And in this case, nothing I've said means that this one has to be the negative of that one. It's not that kind of principal value, but it's only in one direction. But if I do it this way, you will see that I basically get yeah, the best thing might be to split it into 1 over tau plus an order of 1 over tau squared term. That might be the best way. And then this one is convergent, and this one's really explicit now.
Because lambda was gamma plus I tau.
Yeah, but I took the gamma part out of here, but I left it in here. So this is 1 over gamma. Let's see, it's gamma plus I tau minus A. Oh, okay, so 1 over tau, I tau minus A. No, I want this. I want 1 over I tau. Yeah, I want to write it like this. And you'll see that works. Yeah, that's a good way to do it. So all things that we know, but if you look at every detail, it's not so simple. But okay, so what do we get out of this? We get the same conclusion. V of t is bounded by a constant e to the minus theta t, v of 0. Any so for minus theta bigger than a star. And this is the same, exactly the same as what we got from the Jordan-Bloch calculation. Although we actually know more with the Jordan-Bloch, right? We know it's just an algebraic difference, but you know, we know it's not true. It's not true in general that if we tried to put a star in here, that wouldn't be true in general. But from the Jordan-Bloch calculation, we know we only miss by t to the s. And here we've said, well, maybe we miss by arbitrarily small exponential. But okay, but this will be more robust under perturbation to infinite dimensions and unbounded operators. Okay, that's one thing. Okay, so why did I say now? Oh, okay, we don't have to be careful about L, and we don't have to find eigenbases and estimate their size, which would be hard even for a large n. And we're going to try to do infinite dimensions, so that would be very hard. It's often not doable. And yet, okay, we won't be able to do this calculation, but we will be able to estimate the resolvent directly. So that's fine. So this is the preferable approach for infinite dimensions. Okay, so I want to make another advertisement for this and a key point. Okay, so often what you might have might look like this. So again, this is the spectrum of L on the complex plane, and let's suppose I have a nice spectral gap, all except for one, growing mode. And I want to analyze this situation. So what I can do is I can still move the contour. So previously it was Cauchy's first theorem. And now it's his second theorem. It's the residue theorem. So I can do the same business. Out here is operator norm of L. Here is some initial gamma. And I can go right down to gamma star here, which has a negative real part. And I can say that V of t is equal to the same principal value integral of gamma star minus I infinity, gamma star plus I infinity, e to the lambda t, lambda minus L inverse d lambda applied to V of 0. And this is fine, exponentially decaying at rate e to the gamma star t by the same calculations just shown. This part of the formula is exponentially decaying, and what's left is the residue at lambda equals a star of e to the lambda t, lambda minus L inverse. And I just want to point out that, I hope I didn't erase it. I didn't. Here it is. I'm going to erase part of it. This was the derivation. This was the formula. Here I've written out what the Jordan blocks look like after in the not the parts of the resolvent corresponding to each Jordan block. Now, if I take a residue of e to the lambda t times this, so the residue at lambda equals ak, say, there will only be one Jordan block important, the one for, well, it's a star. Okay, of e to the lambda t, and then we have 1 over lambda minus a star, all the way down, 1 over lambda minus a star, 0, and then successive powers. Okay, so when we take the residue, we take the diagonal terms give us just e to the a star t. We just evaluate this part, and then we get a residue of 1. That's what's down the diagonal. Now what happens at the next term? Well, we get the, we should write this out as a series. 1 plus lambda t plus lambda t squared over 2 plus etc. And so here, so far we used this term. Let's see. E to the a star t times e to the lambda t. What have we done here? No, this is what I want. I had it right the first time. Yeah, that is correct. And I want to pull down. Yeah, I'm going to get the derivatives. So I'll get e to the a star t times t, e to the a star t times t squared over 2, and so on. I get exactly the exponential that I did using Jordan form. So in other words, but notice we didn't assume there was a Jordan form. I mean, if there is a Jordan form, then we get this. We get the same result for both. I mean, but suppose you don't know the Jordan form theorem. There's a beautiful theory, and it's exposed in Kato's book on spectral perturbation theory. So that's for unbounded operators. The first chapter is for bounded operators, for matrices, and he does everything in a way that will generalize. And so he shows how you can generate the whole Jordan form and all spectral information, but using residue theory alone. And that's fantastic. That's what you really want. And that, I'm just going to assume that it works as it did in the matrix case without, that would take us too far. But that's a really great chapter to read, and it's very thin. I recommend it. Okay, so in other words, we can get, and so we'll get we basically get that the behavior is the behavior on, it will project you down to this eigenmode, and you get behavior as on that finite dimensional block, which would be like a Jordan form. And then the rest decays exponentially with a nice constant that you don't have to look at the eigenbases of each individual point. You get it all at once just by a resolvent bound. So that's very robust and a very nice bound that you can carry through. Final comment, why stop here? What if I go out to negative infinity? Then what do I get? Well, I get more residues, right? I now get it's actually, I claim that the inverse Laplace transform formula, it encodes the spectral decomposition. And yeah, so we're going to use that. And that one persists even when the spectral decomposition might not. And we'll see that that's what's going to happen. later on for us. Yes.
In this picture, when you have the spectral gap and then you have the
This one here.
no, biggest,
Oh, the previous one where we have a complete spectral gap?
yeah.
Okay, let's see. I may have erased it, but maybe not. Oh, no, here it is. Okay, yeah, this one.
Yeah, you have the radius, spectral radius n, which is to the right. So is this finite dimensional or infinite?
This is for finite dimensional. Yeah.
Why not?
Oh, in the next picture, I do have a residue. Yeah.
but there,
Why do I not? Oh, because I didn't move. I did not. Because you're right. I wrote the. It's a dyslexic typo. Yeah, you're right. I put them in the wrong order. You're right. So here's no, I did not. No, I didn't. I kept to the right. See, I didn't cross it. I didn't cross this. It's to the right of that eigenvalue.
gamma is always to the left of the spectrum. Right?
No, here gamma star is bigger than
But
a
it's
star.
less than modulus of n.
Yes,
Okay.
and it's less than 0. That's the main point.
Okay.
Yeah.
Starting from the right of them.
I started from the right because to define the Laplace transform and get started, I needed to know something. And this was the easiest way to know it, because at the beginning I don't have any bound, but I can easily have this bound. And that allows me to make the inverse Laplace transform anywhere to the right. But then I notice, oh, wait a minute, everything's meromorphic, or in fact, analytic up to here, and it decays fast enough that I can move the contour. So I can have the same formula here.
It's analytic if it was finite dimensional.
If it were, this is finite dimension, yeah.
This is fine.
Oh, why is it analytic? Oh. Okay, so now I'm going back to the explicit formula for the resolvent, which might no longer, okay, so let me just, okay, I just write it again. I'll put it over here. So lambda minus L inverse is the matrix, the adjugate matrix, meaning the transpose of the matrix of cofactors divided by the determinant of lambda minus L. Okay, so this is made, so lambda minus L itself, that's analytic in lambda to begin with. The matrix of cofactors is analytic because I'm taking determinants, just polynomials. That's polynomial. This is polynomial, so I have a ratio of 2 polynomials. But this one is non-vanishing away from the spectrum. So the denominator is fine. It's not 0. As long as I stay to the right of A star. If I stay to the right of real part equals A star. So this, yeah, and the modulus of L is unimportant for me. That was just like a convenient starting point, easy starting point. But it doesn't have very much to do, as we know, with the spectrum. It could be quite different. So it's not sharp. But now using this observation, that now allows me to move anywhere. Because it's a contour integral of an analytic function, I can move throughout the plane. Let's see, in finite dimension, would it be, sorry.
I think that is
I'm thinking of am I in the wrong order here? Let's see. No, because for example, a Jordan block with eigenvalue 0, the matrix norm is not 0. Matrix norm is bigger than the biggest eigenvalue. If it were self-adjoint, yes. Yeah, so the self-adjoint case, I would be sharp already, I guess. I could do it by an energy estimate. Yeah, and that's how I'm imagining getting this. That's the point, right? Because they would call it, yeah, these things shrink to nothing in the self-adjoint case. Yeah.
star could be on the other side, right?
Could be on the other side, right? And that was supposed to be, where did it go? The picture that I think is below this. Yes, that's this picture. Yes, this is the American. Yeah. And if it's on the other side, now we want to throw away exponentially decaying things, but we have to keep everything. Maybe there are more. We would keep them too. They would be less important than this because they would relatively they would be decaying exponentially, and we would get all that pretty explicitly.
Is there a reference for all these analyses? So even the ODE, I mean, the ODE that you.
The ODE and things. I wrote some ODE notes that are on archive. I never.
On your page of.
Yeah, on my math archive page. Yeah, it's there, and there's a section on that. Before.
Because it's kind of subtle, though.
Yeah, yeah, it is. Yeah. Surprisingly subtle. Since it's used all, if you're just happy just formally moving things, you get the idea very quickly. But if you want every detail, subtle. And the trouble is, when you go into more challenging cases, these subtleties might result actually in a difference in the formula. It might be the wrong formula if you leave something out of solve.
So now we are essentially in a good shape to generalize to the infinite dimensional case.
Yes.
Right? Because this rationale works.
Right. But notice something tricky is right here.
Oh, yeah.
I don't have this. And I used that to move the contour. So what am I going to do instead? Well, yeah, it's actually very, very simple. And
Yeah.
it's in all the semi-group resolvent identities is how you do it. But it's very clever also. It's not obvious. But yeah, so that's one of the things we'll fix up. And another thing is we have this, it didn't come here yet, but no, actually it's already in here. There is kind of a loss of derivatives that you'll see when L is unbounded in the formulas, in the bounds themselves. And yeah, I mean, that's why a book on semigroup theory looks like this, and a book on Laplace transform it's like this. Very short, finite dimensions. Yeah. Okay, so I think we're just time for that's exactly what I wanted to do. Amazing, and yeah, so stop there. Are there any questions from out in the void there? No? Yes? Oh, hi, Jim. Yeah, all good. Could you read better this time? Better? A little better? Okay. I think it still needs to be bigger. Probably. Okay. Well, we stop here. Go IU. Does anyone know what I'm referring to? Our football team won the national championship of college football last night.
It's now that's happening.
It just happened, yeah, yesterday evening.
So at this point of the winter,
Yeah, that's weird. Why is it on a Monday? That's very unusual. But probably some advertising issue. Yeah. Okay.
So you could see it? You
I
have a TV in your apartment?
No, I couldn't get. I decided to try a free trial of TSN, but I couldn't get it with an American credit card. Luckily, there's a sports bar just below my apartment. I was saved with all kinds of network. So I don't watch many games, but for this one, I wanted to watch.
Because it's the team of Bloomington.
It's the team of Bloomington. Yeah. No, in fact, I don't watch any games, including the Bloomington. I watch by looking at the score on my phone, but.
But in Toronto, because it was a big thing with the baseball. Even me, who never watched anything, I heard so much. people were crazy about it.
Yeah,
In
they
schools.
almost did it. They almost.
In schools, in the streets. So it was, I don't know.
No. My colleague Peter Sternberg, who comes here. pick up.
Yes.
Yeah, he's crazy for baseball, so he would have liked to be here then. But he was for the other team. Sorry.
Doesn't matter.
Okay.
You're going to.
Yes.
Yeah. Oh, that's it's mostly tricky, but it's in between things that extra hours, so you get to start being all.
Oh, yes.
Yeah. Things that you don't know. Right, Chris, balance.
That's great. Thank you. Let's see tomorrow. Thank you very much. See you. See you.
See you soon.
See you. Yeah. Let's hope tomorrow we come.
Professor,
Hi.
thank you. Thank you so much for the bigger writing. It really, really helped.
Oh, good. I'm glad.
Yeah.
This is good training for me.
Yeah.
Like, really think every line, but you should.
Yeah.
Yeah.
Thank you
Well,
so
thank you
much.
again. See you Thursday.
Okay, see you.
Bye.
Bye.
Bye.